All right, welcome back. I keep having to fight my internet in the morning for some reason. Sorry, I'm a minute late. All right. We were at example 2B. Yes. Okay. So this is still 7.2, which was the law of cosines. And I'm just going to write one of the versions of these up here in the interest of time. So it was a squared is equal to b squared plus c squared minus 2bc times the cosine of angle A. And then there were the two other versions, b squared equals da 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 da, and c squared equals da 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 da. So basically the same thing, b squared's got a's and c's, where c squared's got the a's and b's in the same exact type of pattern up there. And we did examples 1a, b, and c, and those were all side angle side cases. So we said this is for side angle side or side side side. And then we also had to make sure that we never use the law of sines to attack the largest angle. And that was because if that angle is oblique, if it's bigger than 90 degrees, the law of sines cannot find an angle that's bigger than 90 degrees. It can only find angles that are from negative 90 to positive 90, and we're not going to find any negative angles in these either. So that's when you absolutely have to use the law of cosines if you're trying to find the biggest angle, or 180 minus the first and second. Okay, so let's go to a new screen. And we're picking up where we left off with example 2B. So we're going to draw this triangle. And again, never assume that the way I draw the triangle is what it looks like, because this looks kind of equilateral, but it definitely isn't with those given sides. Okay, so I haven't designated these sides as A, B, or C, but I'm going to end up calling the angles just by my choice. Let's call this top one angle A. Let's call the bottom left one angle B, and then the bottom right one angle C. Now remember, these could be alpha, beta, and gamma. Sometimes we'll use the Greek letters, sometimes we'll use the capital letters. So we want to make sure, and this is the side, side, side case, because I gave you all three sides. I didn't give you any angles. So you have to use the law of cosines to start. We always end up coming back to the law of sines. But we want to make sure that when we get to the law of sines, we're not approaching the biggest angle because of the thing I just said. It could be oblique. It may not be. It depends. So we want to make sure we go ahead and find the largest angle first by using the law of cosines, because the law of cosines can give us an oblique angle. 18 is the largest, so we need to find A first because 18 is the largest. All right. So since we're supposed to find angle A, we need to use the version with angle A in the formula. So that would be one we just wrote. Sorry, I'm still getting organized as I was fighting my modem. All right, so the one we wrote before was, again, a squared equals b squared plus c squared minus 2bc cosine angle A. Okay. So the a squared is the 18 squared. equals the b squared, well, that's the 10 squared, because it's opposite angle b. And then plus little c squared, that's opposite angle c, so that's the 15 squared. Then minus 2 times 10 times 15 times the cosine of angle A, which we don't know. That's the unknown. So this is not solved for the thing that we need right now. We need to go through the process of solving for A. So 18 squared is going to be, what's that, 324? Equals 10 squared is going to be 100. Sorry, 15 squared, what's that, 225? Minus 2 times 10 is 20. 20 times 15 is 300. So that's cosine A. The 100 plus the 225 is going to give us 325. That's a terrible looking equal sign. Then minus the 300 cosine of angle A. We cannot do the 325 minus the 300. A lot of people make that mistake. You have to be careful because these are not like terms. This has that cosine. So we have to move the 325 by subtraction. Which is going to give us -1 equals -300 cosine of angle A. And then we're going to need to divide both sides by the -300. To give us, well, the negatives will all cancel. So that's a +1 over 300 equals, leave a little space, cosine of A. So if we have the cosine of an angle equal to a number, that means the angle is the inverse cosine. Now again, some people will go straight to that. Some people show the step of taking the inverse cosine of both sides. It's up to you whether you show that step or not. I like to see it. So that inverse cosine of 1 over 300 is equal to A. And we're going to round this to the nearest tenth. We're going to put that in our calculator. Give me a second. Share calculator. All right. So we were typing the inverse cosine. Let's check our mode. See, this digital one resets every single time. So I have to always make sure I go back to degree. Second quit. And I'm doing inverse cosine, so second cosine of 1 divided by 300. 300. And we get 89.809, which will be 89.8 degrees rounded to the nearest tenth. So that's almost 90. 89.8 degrees. That's our angle A. Oops. So angle A, I mean, that is almost a right angle. It is so freaking close to being a right angle. Now, what's interesting is if you do this stuff over and over and over, if you start recognizing patterns and what things are going to be, you will ultimately know that this is going to be really close to 90 degrees. Well, why is that? Because 1 over 300, I mean, that's pretty much 0. That's like 0.01 or 0.02 or something in that ballpark. And the inverse cosine of 0, well, we're looking for an angle that would have the cosine be 0. In other words, its x-coordinate be 0. Well, the x-coordinate is 0 at 90 degrees. That's also true at 270, but inverse cosine is not bound or not valid inside of that bound. The same thing works if this thing was really, really close to 1. If this was like the inverse cosine of 0.99, I would know that that was going to be very close to 0 degrees because I'm pretty much taking the inverse cosine of 1 and the x-coordinate is 1 at 0 degrees. So these are just little things that we like our students after they've been through this, been through calculus, that they start being able to do on the fly. So now that we have our first angle, we have angle A, we can approach angle B or C. Now A was the largest, so it doesn't matter which one we find next. I'm gonna go for B. So we're gonna use the law of sines next. And again, it doesn't matter whether we tackle angle B or C next, I'm gonna go for angle B. We have the A's completed. The side length is 18, the angle is 89.8. So we go 18 over 8, not 89.8, the sine of 89.8 degrees equals, and we're going after the B's, so length B, which is 10, over the sine of angle B, which is unknown. And we're going to do the exact same algebra and trig that we've been doing for this law of sines. It's only two variations of it. Cross multiply, we get 18 times the sine of angle B equals 10 times the sine of 89.8 degrees, which the sine of 89.8, that's pretty much the sine of 90. The y-coordinate of 90 is 1. So this guy right here is 1, which means the 10 times that is going to be almost 10. It's going to be really, really close. Then we're going to divide this by 18, which will give us the sine of B is equal to, and again, I'm not going to worry about the reduction because it's going in a calculator. Let me leave myself a little room. 10 sine of 89.8 degrees over 18. And since that says sine of B equals, and we want the B, we take the inverse sine of both sides. And remember, this only works if you're in the appropriate bounds. So it only works if you're between negative 90 and 90. Another reason as to why we have to make sure we're not using the angle. And we've seen this. I did an example where it was wrong last time. We did it right as well, of course. So B is the inverse sine of 10 sine 89.8 degrees all over 18. And that's what we jam in our calculator and round to the nearest tenth. Where's my mouse? There we go. So inverse sine of 10 times the sine of 89.8, close the parentheses, 89.8. That probably wouldn't even have made a difference in rounding to the nearest tenth, but let's be careful. Divided by 18, close it. And we get 33.7 rounded to the nearest tenth. It's almost 33.8. I'm almost curious if that would have been different. I'm curious. Second enter. What if I had 9? What if I had that typo left in there? Would we have gotten the same answer? Just barely. Just barely. Again, let me clear that so you don't think that's what we're using. That's what we used. So 33.7. degrees. And then we can find the third angle by doing 180 minus the others. So angle C, or gamma, would be 180 degrees minus the 89.8 degrees minus the 33.7 degrees, which makes angle C, what's that, 90.2 minus 33.7, that's 56.5 degrees. So we were given 3 sides, and now we have our 3 angles, and that's all we have to do. So I'm going to give a quick summary on the next page in about 10 seconds as to the law of sines and cosines jazz. When to use what. All right, so we use the law of sines to start when we're given side angle angle, which is the easy case, or side side angle, which is the hard case. Side angle angle, you go ahead and attack the first angle, then you can get the other side, another side by doing law of sines, and then another side by the law of sines. Side side angle, that's where we had the ambiguous case. We said that it was no triangle if the calculator gives an error. Specifically on a TI-83, it says error domain. I can't promise that's what it says for some other random calculator. It might just say undefined, does not exist, something like that. But you're going to end up doing an inverse sine of a number that's too big, something like that 1.5, which is outside of the range of a regular sine, so it's outside of the domain of an inverse sine. So that's what we did with the side-side angle case, and we came up with that note later that we said never use the law of sines to find the largest angle. This is something that people forget all the time and end up getting triangles that look correct but are actually incorrect. Okay, there is a second triangle if the supplement of the second angle, which is the first one you find, plus the original first angle is less than 180 degrees. It had to be small enough to make another triangle with the other version of it. And the supplement of the first angle you find is the second version. Okay. For law of cosines, we use the law of cosines for side angle side or side side side. And the distinction between side side angle and side angle side, I said that this was a corner of info. So it's something like, we know that side, we know that angle, and we know this side. And then the angle here is unknown, the angle here is unknown, and that blue side is unknown. So everything that touches the blue is unknown, everything that touches the red is known. And same thing, we want to go after the largest angle first in the side, side, side case. This is an optional technique in that there are other ways of making sure that you don't screw this up. Some people will say you can just make sure that you find the largest angle by doing 180 minus the first two that you find by law of cosines and law of sines, and that works as well. It's just a lot more common to go after the largest angle first because that's what we've done classically. But what I just said previously, and I don't want to say it too many times so I don't confuse you, but that would work as well, because you would guarantee that you're not trying to use the law of sines to find the largest angle. So just one more reminder about those inverse trig functions. Inverse sine can get angles from negative, 90 degrees to 90. Inverse cosine can get angles from 0 to 180. Oh, these should have degrees on them. That's why we cannot use the inverse sine to find an angle that's oblique. All right, next up, And this section has changed section numbers every single time we've had a new edition for one reason or another. I'm not exactly sure why. It doesn't matter. Doesn't mean anything's different. .6 vectors. All right, this right here opens up an entirely new field of mathematics. And I don't mean new to the world, I mean new to you. Vectors, and we're not going to dive too deep into this topic. I mean, we're going to cover a decent amount of material, but we're not going to go too deep because this subject, I mean, there are entire graduate level mathematics courses on vectors. Hold on, before I get to that, let's just give a couple definitions. And let me pull out the text just to make this a little neater. So, a couple definitions. A scalar. A scalar is something that we've dealt with all semester, believe it or not, whether we've known what it was called. A scalar is a number that only has size. Whereas a vector, the namesake of the section, is a number that has size and a direction. So a scalar is just a number. Everything we've dealt with in this course so far has been a scalar. Everything that you've dealt with in Pre-Calc 1 has been a scalar, when there were numbers, not variables. Everything that you dealt with in Algebra 2, Algebra 1, in pre-algebra, in arithmetic, those were all scalars. A vector is a number that has size and direction. Now, there is a basic concept, a pair of terms that show the difference between scalars and vectors in the real world. And they are speed and velocity. Speed only has a size. So something like 55 miles per hour. So when I say I'm driving 55 miles an hour, I'm certainly not walking 55 miles an hour. If I say I'm driving 55 miles an hour, I'm telling you how fast I'm going. That's a size. But do you know where I'm heading? No. I might be heading east. I might be heading northeast. I might be heading 10 degrees due south from west, which I did not say in appropriate order. Hold on. South 10 degrees west is how I should say it. So you can't tell what direction you're going when you say a speed, but a velocity, this is a pretty early on physics term. This has a size and direction. So this would be me saying 55 miles per hour, let's say just due east. So speed tells you how fast you're going, but velocity tells you how fast you're going and a direction. Now in math class, we're not going to be using due east or anything like that. Generally speaking, we're going to use, probably no surprise, angles. 10 degrees, 50 degrees. You can go negative if you really want to. All right, back to drawing. So what does a vector look like? It looks like this. It looks like an arrow with a dot for a tail, typically. Now, does this dot always get drawn? Quite honestly, no, but you definitely have to draw the arrows. So this dot is what we call the initial point. And then the point that the arrow is placed at is what we call the terminal point. So we have an initial point and a terminal point, and we have to put our arrow facing the terminal point. So this is what a vector looks like. Not question mark, that's a colon. They always end up looking like that with this thing. All right, well, guess what we can do? We can call this right here the hypotenuse of a right triangle. We can do a little horizontal line, a little vertical line. We can make a right triangle out of the sky. And then we can find what are known as components or the magnitude, depending on what information we're given. So let me go back to text. We can find the magnitude, also known as the length, just a fancier term for length, by the Pythagorean theorem. So there's two different notations for this. We denote the magnitude I'm not going to be able to type this next bit, which is why I'm doing this. It looks like an absolute value, but there's two of them. And then that's the letter V, but I'm really trying to emphasize that it's bolded. So that is a bolded letter V. Hold on, I'm going to mute for a second because I got to cough really bad. All right. So that's one way to write this. Or you can write this as a double absolute value with just a regular looking V, but then you draw a little arrow over the V. So there's an arrow over the V. So these are two representations of magnitude. So what I'm telling you here is that vectors themselves have two different types of notations. They can be a bolded letter or a letter with an arrow over them. Now, typing, it's really easy to hit Control B or the B key, but it's really hard to do vector math typing half of the time. So this is not the notation I'm going to use, but you will see that littered all over your textbook. They'll be using in the homework problems. They'll mix up both notations. So I'll try and use this occasionally since it's not too difficult to make it bolded looking with this. But I do prefer the arrow notation personally. So again, vectors will look like a bolded letter or just a regular letter with a little arrow over them. And then sometimes you'll see teachers not write the bottom half of the arrow. They'll just do it that way. I'm a big fan of that way because that's how pretty much all my math teachers did it. So vector notation has a bolded letter or a variable with an arrow over it. Scalars, it's just a regular V. Not bolded, no arrow over it, nothing. So I mentioned that we can use the Pythagorean theorem to find the magnitude if you know the components. So let's just redraw that vector without all the words. And let's say that we knew this distance right here. If we knew this distance is A, and then if we knew this distance, this vertical distance is B, I could call the hypotenuse of that right triangle C, and then guess what? A squared plus B squared is equal to C squared. But the magnitude, the length is C. C is the magnitude of the vector. So instead of writing C right here, I can just write it as the magnitude of the vector. Again, with components, its horizontal component would be, you can call it A, and you don't have to call it A. And then the vertical component, we'll call it B. It doesn't have to be B. Just give them letters, numbers, whatever. But again, the key is we can find the length of the vector by the Pythagorean theorem, and this is going to be a pretty common theme. So let's try this out with an example. Well, not yet. Can I get that up here? Yes, I can. All right. If you're given points for the initial and terminal points, you can subtract them to find the lengths. So let's go back to that drawing we just had up here, and let's actually call them points. So this initial point we'll call x1, comma y1, and then the terminal point right here where the arrow is pointing, let's call that x2, comma y2. Well, A is the difference of the x values. This is just the change in the x coordinates, the same way you would find slope. And then B would be the difference of the y values, again, the exact same way you would find the height change for slope. So that's doing x2 minus x1 and y2 minus y1. And then one final little memo real quick. Asterisks, because this is important. Two vectors are the same if their magnitude and direction are the same. The same. Two vectors are identical if their magnitude and direction are the same. So here is the fascinating part about vectors. This statement right here. The initial point and the terminal point of vector 1 does not have to be the same as the initial point and the terminal point of vector 2 for them to be the same. For two vectors to be the same, all it has to be is that their lengths are the same and they are pointing in the same direction. Now, if they're pointing in the same direction, that means that the angle formed if you made a little right triangle would be identical. So in other words, their lengths and angles have to match. It doesn't matter where they start and where they end, as long as the lengths are the same and the angles are the same. So this little vector right here, here's its initial side and here's its terminal side, and it's sitting over here, obviously. And now I'm going to draw this one way over here, and I'm going to draw it such that that doesn't look like the same angle. Let's make sure it looks like the same angle, Rodney. That looks a little better. So I'm going to say that those lengths are the same and their angles are the same. So those two red vectors are the same. It doesn't matter that this one's over here and this one's over there. They're the same length. They're pointing in the same direction. They are the same vector. You can take a vector and you can uproot it and you can put it over here, or you can put it over here, or you can put it over here. It does not matter where a vector starts and ends as long as you keep its length and the place and the way it's pointing the same. So you can what's the word I'm looking for? Not translate, not transpose, transfer. You can transfer a vector from one location to another and you're not actually changing it. And that's something that we will do. All of this might sound like a lot of complicated math. It's really not. You're going to see that the example we do in a minute is quite easy. All right, so example 1, let's say prove the vectors are the same. So I'm going to draw this up in a coordinate system. And let's go left, 1, 2, 3, and down, 1, 2, 3. We'll have a point here. I wish I'd done all this in black. Oh well, no big deal. And then we'll have a point up, 1, 2, 3. And these 2 points will form a vector. And I want to have it pointing up and right. So there's our first vector. Now each of these are incremented in 1, so that's -3, -3, and +3. And then let's have another vector, and I'll change colors for this one. Let's do it in blue. Let's have a point at the origin. And then let's have a point at, oh no, I did not do this well. I need to have this a little higher. I need a little more vertical space here. Sorry about this. Prove they are the same instructions. I just needed a little more verticalness. I apologize. Nothing's going to change with what we had though. So that was left, 1, 2, 3, down, 1, 2, 3. There was our initial point. 1, 2, 3, 4, 5, 6. There's our terminal point. And there's our vector. And then for the next one, it's going to be at the origin. And then at the point 3, 6. So there's our vector. It's pointing up. Okay. So we're going to prove that these vectors are the same. Well, I'm already telling you they're the same, but we got to prove it. I need to see the math. So if you want to label these coordinate pairs, that's the point -3, -3, the initial side of the red one. This would be the point 0, 3, the terminal side of the red one. Then for the blue ones, that point is the origin, 0, 0. This point would be 3, 6 for the initial and terminal sides respectively. So to prove these two vectors are the same, we have to do the very last thing that was mentioned on the last page. Two vectors are the same if their magnitude, in other words, if their length and their direction are the same. Why do I have a blank page? That was weird. I must have hit the plus page button. Always fun. Red. So for vector 1, the red one, and you can give these variable names. You can call them v and w if you like, or x and y if you like. I don't really like calling them x and y because the axes are labeled x and y, but since you'll be giving them vector notations, in other words, the little arrows with them, it wouldn't be the worst thing in the world. So the x length, that's the horizontal change. That's the difference of the x's, which is, well, this x value is 0. This x value is -3. So 0 minus -3. Again, that's just x2 minus x1. Come on, let me move this thing. Why won't you let me move it? There we go. Again, that was x2 minus x1, and I'm not going to show that for all of them. That's 0 plus 3, which is 3. Then the y length would be the difference of the y values going in the same order. Arguably, you can't actually screw up the order because of the way Pythagorean works, because we're going to be squaring negatives. So the difference of the y values, the y2 would be the 3, the y1 is the -3, so that's 3 minus -3, which is 3 plus 3, and that's 6. So instead of writing vector 1, let's denote that with that bold. I'll use the bold this time. And then I'll give it a little 1. So this is vector 1's information. It has an x length of 3 and a y length of 6. So it went right 3 and up 6. So no matter where you draw that vector, if I want to start right here, as long as I go right 3 and up 6, this right here is literally the same vector as that one. Now, I didn't actually go up 6, so it looks shorter. I'm just saying that no matter where I start, as long as I go right 3 and up 6, I end up making the exact same vector. All right, so let's find the length, the magnitude. That is a v, not a y. So the magnitude of v1, the length of the vector. Again, this is just Pythagorean. So if you drew this up, this horizontal component would be 3. That length is 3. And then that vertical length would be 6. So 3 squared plus 6 squared would be equal to this thing squared. You're going to take the square root of both sides. No surprise there. So square root of 3 squared plus 6 squared. Which is the square root of 9 plus 36, which is the square root of 45, which we still prefer analytic answers for things that aren't inverse cosines of 5 times inverse sine, blah, blah, blah. We can break this up. We can't take square root of 45 though. We can write that as the square root of 9 times 5, and the square root of 9 is 3. So 3 square root of 5 is the length of vector 1. And yes, that has a decimal approximation, but that's not what I'm caring about right now. Let's go to vector 2. Which we'll denote as bold V2. So it's x length. Again, it's just the difference of the x components, which are 3 and 0. And 3 minus 0 is 3. Then the y length is the difference of the y components, which are 6 and 0. 6 minus 0 is 6. Now, some people would say, oh, okay, well, the x and the y lengths are identical for each of these, so that proves that they have the same magnitude. Right 3 up 6 is the same as going right 3 up 6. How would you ever get a different length on the hypotenuse if the components are the same? Also, some people will claim that this proves that the direction is the same, but we have to take this a little more seriously, so we're going to have to find a way to prove that the direction's the same, just to be a little more meticulous. But we're not there yet. So the magnitude of vector 2 is the square root of 3 squared plus 6 squared, which is definitely the square root of 9 plus 36. It's the same math. You end up with 3 square root of 5, which is the same. So we have shown that the magnitude of vector 1, bold V, is equal to the magnitude of vector 2. In other words, the lengths are the same. But what about the direction? Again, a lower trigonometry class, if this wasn't pre-calc, if we were just saying geometry, introducing vectors, we would say this is good enough. How can we prove that the angle is the same? Well, there are ways, but for now, let's just think about it this way. If the slope of this line is the same as the slope of this line, then the angles would have to be the same, because slope is just another way of saying angle. It's just a different relationship. So let's find the slopes. M's slopes. Slope is the ratio of the change in y to change in x. It's y2 minus y1 over x2 minus x1. So for the first line, we'll call it M1. That's y2 minus y1, which is 3 minus negative 3, over x2 minus x1, which is 0 minus negative 3. which is 3 plus 3 over 0 plus 3, which is 6 over 3, and that's 2. The slope of the second line, and notice the 6 and the 3 are the same thing that you came up with here, the 3 and the 6. 3 and 6, the 3 was the x, the 6 was the y. So some of you may just go ahead and say, oh, okay, well, I already know what those differences are. It's the numbers that I saw in the magnitude, so let me just use that again. So spoilers, the 3 and the 6 are going to be used here ultimately. But let's show the actual work. Y2 minus y1, that's 6 minus 0 over x2 minus x1, which is 3 minus 0. Look at that, 6 over 3, which is 2. So m1 is m2. So vector v1 is literally the same thing as vector v2. QED. Quod erat demonstratum. Proofed. Done. Finito. There was no crazy trigonometry to be done here. Again, this is actually something that we can introduce in a geometry class, and often some teachers do. We just don't really have geometry in colleges. We just tend to go algebra than trig. Now, that doesn't say that we're not going to do any trig with this stuff. We absolutely will. But let's hold on to that for a few minutes. How are we on time? 8:48. Okay. Next up, scalar multiplication. Let me pull out the text box. Of a vector. Scalar multiplication of a vector. So what I'm saying is if I give you a vector, something like the 0, 0 pointing at 0, 6, if I multiply that by a number, what happens to it? Well, it changes the length. That's all a scalar multiplication of a vector does. So again, the point we were making in this last example was that these red and blue vectors were the same. So it doesn't matter where it starts and ends, as long as it has the same length and the same angle or the same direction. Angle, direction, those mean the same thing. So this red dot I could put right here at say -2, 4, and as long as I go right 3 and up 6 from there, and I'd end up at, what is that, 1, 10, that new green vector would be the same as the red, would be the same as the blue. I can draw this 10 billion different ways. So if I take a vector and I say multiply it by 2, that's going to double the length. If I multiply it by a half, it's going to half the length. If I multiply it by 17, it's going to make it 17 times as long. So scalar multiplication of a vector simply changes the length. Oh no, that's silly. That's okay. But if the scalar is negative, let me make this a little bigger, comma, it rotates the vector 180 degrees. In other words, it points the opposite direction. Can I make bold letters? Nope, I cannot. Okay. So the thing I said earlier, let's write that down. So i.e., given a vector v, and I'll do it with the arrow notation this time, 2v would just be twice as long. 1/2 v would be half as long. So let's draw up a couple of pictures for fun. So let's say This right here is our vector v. Again, I'm using the arrow notation for this time. Now I'm gonna have to, I can't actually measure this, unfortunately. I'm gonna do this to the best of my ability. Let me see. 1, 2, I'm gonna say it should be about here. There we go. So let's just say that this length right here was 5. I'm trying to pretend that this length is 10. I have drawn this perfectly such that its length is 10. And if this angle right here was, say, 10 degrees, this angle is also 10 degrees. Or if this slope was, say, a third, this slope is a third. So I'm trying to say that these are the same angle, but the other one is twice as long. So this would have to be 2 times the vector v, or 2v. Or, again, let's say this length was a half. The vector I'm drawing here is going to have a length of, I'm sorry, let's say this length was 5, not a half, excuse me. If this length was 5 originally, I'm now drawing something that has a length of 2.5. So this would be 1/2 times the vector v. Or, let's say I draw something that's the same length, but instead of the arrow pointing up and right, let's have the arrow pointing down and left. This would be negative v. That's what we mentioned here. If the scalar is negative, it rotates the vector 180 degrees, which just points it in the opposite direction. So again, this is pointing in the opposite direction to the original one. It's the same length, but pointing in the opposite direction. And we're not just going to double or half or negative vectors. We can multiply these by any value we like. Positive, negative, whole, fractions, it does not matter. Rational, irrational numbers, all those don't matter either. All right. Next up, the unit vector. This is arguably the most important type of vector in the whole world, a unit vector. The word unit typically means something, there's one of something. Now, yeah, you know, oh, a unit's like a meter or a foot or something like that, but it's all based around how big is one of these things. So again, in terms of a number, unit means one. So a one vector, what that's saying is that we have a vector with a length of 1. So a unit vector is any vector that has a length of 1. Now, do most vectors have a length of 1? No. But what we can do is, if we're given an original vector, if we break it out and break it down into its components, like its x value and its y values like we saw previously, we can create a unit vector that points in its same direction. And that is quite often very, very helpful. But before we get into doing that complicated mess, let's talk about the two base unit vectors. I and j. So we have two unit vectors, I and j. I'm going to draw up a coordinate system. I don't need that one to be that long. A little better. X, Y. And this is going to be super zoomed in. So that's 1 on the x-axis, and this is 1 on the y-axis. And in red, I'm going to have an initial point at the origin, and I'm going to have a terminal point right there at 1, 0. So that red vector right there is the vector I. And that is a bolded I. Let me just kind of emphasize that. That is a bolded I, because it's a vector. The vector j starts here and instead points up at the point 0, 1. That is the vector j, and again, I am bolding that as best as I can. Let me make the I a little prettier. There we go. These are the two most important unit vectors of your life. There's a third one when you get into 3 dimensions, it's k, and that's when you have a z-axis, and k just points at 1 on the z-axis. So these are going to be the basis of us writing vectors in component form traditionally. So I is the base horizontal component, and I'll write it with an arrow this time. And some people don't even do the dot, they'll just put the arrow where the dot would be, like this. So I is the base horizontal unit vector. J is the base vertical unit vector. We're going to use these a lot. So with vectors, we saw an example previously. Oh, there it was. Here is this vector. It started at -3, -3, and it pointed at 0, 3. But we said it was the same thing as if we had it starting at the origin and pointing at 3, 6. We don't necessarily want our vectors just lying around in random places. If it's the first vector, we typically like to have it at the origin. If it's a second vector, if we're doing some math with it, we might want to have it somewhere else, but maybe we want all of our vectors starting at the origin. So it's actually really beneficial just to think about all of our vectors having started at the origin, and then however far right it goes would be the x component, however far up it goes, or left or down, would be the y component. And whatever those numbers are, we just slap i's and j's next to them, and that gives us our notation. So we can represent any vector with scalar multiples of I and j. And just pretend that those are bolded, please. Please pretend that those are bolded or have arrows over them. So having a unit vector, having something that's just a length of 1, so if we need to have a length of 3, we just need 3 of those lengths of 1. So that would be like a 3i or a 3j. So this gives us the standard form for a vector. It's ai plus bj. Again, the I and j are bolded or have arrows over them. Where we call A the x component, because that would be however far left or right you're going, and then B would be the y component, because that would be however far up or down you're going. Where the magnitude of the vector v is the same thing from before. That Pythagorean theorem, the square root of a squared plus b squared. Again, that is just lifted from a right triangle where a and b would be the legs if you drew it up as a right triangle. So seeing a vector in standard form is awesome, because if you start the initial point at the origin, it tells you exactly what coordinate the terminal point would be at. And like I said, we really like to write our vector starting at the origin for that convenience. So I'm going to type up what I just said. In standard form, you can start the vector at the origin, and then A and B give the X and Y coordinates of the terminal point. Ten minutes. So again, believe it or not, the math that we're going to be doing with this stuff is super simple. I honestly think that this section is a break after doing law of sines and law of cosines with all those weird different cases, having to make sure we do things in a specific order. Otherwise, we can screw it up. This is just going to, for the most part, look like basic algebra, and then a little bit of light trig thrown in at the end of the section. All right. So what are we up to? Example 2. Why does it keep switching back to red? Write the vector in standard form. There we go. Write the vector in standard form. And this is 2A. I'll write the A after I do this. Given by starting point of 1, 5, and a terminal point of 8, nope, wrong one, 4, negative 7. Again, this is A. So we got a vector that starts at 1, 5 and is going to point at 4, negative 7. But if I know the length and its direction, I can just put that wherever I want to. It'd be really nice if it started at the origin. And the good thing is, if I find the components, the length of the horizontal and length of the vertical, that tells me exactly where it would point to. So A, the X component, that's just the difference of the X values. Well, the X value of the second point is 4. The X value of the first point is 1. 4 minus 1 is 3. That's it. The Y component, we said we'd call B. That's the difference of the Y values. And if you need to draw this up, you can. But it's just the difference of the Y values, which are negative 7 and 5. But you got to make sure you're consistent with the order. So that's negative 7 minus 5, the second minus the first, which is negative 12. That's it. We're done. That's the whole problem. So our vector V, whether you write it with bold or with an arrow on the top of it, it's AI plus BJ. So 3I I'm going to do it with the arrow, and then minus 12J. Or if you do it with the bold notation, the vector V would be 3 bolded I minus 12 bolded J. This just gets really tedious. Which is why I prefer the first one, but the second one is the same exact answer. So again, starting at 1, 5, that's right 1, up 5. And then we're pointing at 4, negative 7. So 1, 2, 3, 4, negative 7. That's here. So this is the original vector. But that would be the same thing as if we started at the origin. So the red will be the answer if we start at the origin and we go right 3 and down 12. So right 3 down Let's just extend this. Let's call that negative 12. So write 3 down 12. Oh, wrong color. And I did this super quickly, so it doesn't quite look like the exact same angle, but those are the same. Just pretend like I drew that perfectly. So again, this version gives you a very easy vector to draw. You don't have to draw a starting point and a terminal point. You draw your starting point at the origin. Your terminal point is the numbers in front of the i's and the j's. The I tells you the x, the j tells you the y. And if you have a hard time getting those straight, x and then y, I and then j, they're both in alphabetical order. Let's try another. Let's have a starting point of negative 4 comma 3. And let's have a terminal point or ending point at 8 comma negative 2. All right, so A, the x component, it's the difference of the x values, the terminal minus the start. You have to go terminal minus start. You cannot swap these. You have to go terminal minus start. So it has to be 8 minus negative 4. This isn't like slope or the Pythagorean where the order doesn't matter. It absolutely matters here. And the slope order matters in that you have to be consistent. So that's 8 plus 4, which is 12. Then the B, which is the y component, that's the difference of the y's, terminal minus start, so negative 2 minus negative 3, which is negative 2 plus 3, which is 1. So our vector, and I'm just going to write the arrow notation this time. 12 and the 1 are the numbers that go in front of the I and j. So 12i plus, I'll write the 1 initially, but most people are not going to write that j. I mean, most people are not going to write the 1, excuse me. You have to write the j. So that's 12i plus j. You really are not supposed to write the 1 because it's not simplified with it there. I wouldn't mark it wrong on a test, but my math lab probably would. So be careful there. So this tells you that wherever you start, just go right 12 and up 1, and then there's your vector. So I could start it here, go right 12, up 1, there's my vector. Or I could start it at the origin, which would be super convenient, and go right 12, up 1, and I could tell what the terminal point was very easily, 12 comma 1. Let's get into vector math next class. I want to leave you with an alternative notation that, depending on your teacher, depending on your textbook, you may or may not ever see. So I want to make sure that you at least see it with me, because I like to make sure we get all our grounds covered. So an alternative notation. AI with a vector plus BJ with a vector is the same as A comma B inside of sideways V's. This kind of looks like a coordinate point. It kind of looks like a coordinate. Coordinates would be parentheses. These are not parentheses. These are sideways V's. You know why we use sideways V's? V for vector. So A comma B is a point just at going right A and up B, or left and down, or whatever it might be. But if I use this, that's a vector. So AI plus BJ is literally the same thing as what looks like a coordinate A comma B, but with a less than and a greater than on the outsides of them. So that last example, we said that the vector was, I believe, 12i plus j. We also could denote this vector as, between these sideways v's, 12 comma 1. So that is the same exact thing. For A, we had 3i minus 12j. That would be the same thing as if I went 3 comma negative 12, and I had them surrounded with those I'm sorry, not absolutes, those less thans and greater thans. Someone is knocking at my door. What do you want? So we're going to go ahead and call it a day there. We have not finished this section. I would say we haven't even come that close to finishing the section. We've got quite a bit more material to do next class. But besides that, have a good weekend. This will go up on YouTube no later than noon. I'll be uploading it right after my next class. I'll have the link in Canvas. Remember, all that old stuff goes in Canvas in case I go too fast anywhere, you need to see something again. The one benefit of us not being in the classroom is you can rewind me, so that's awesome. Keep up with your homework, and yeah, we'll call it a day. So have a good one, have a good weekend. We'll see you next time on the internet on Monday.